Hi, everyone. We're going to start now the webinar. I'm Tamar Gal, Iguazio's marketing manager. Thank you for joining us today. We're going to talk about cutting time, complexity, and cost from data science to production. Our presenters today are Yaron Haviv, Iguazio's CTO, Or Zilberman, data scientist at Iguazio, and Jacci Cenci, our senior technical marketing engineer at NVIDIA. So today we're going to go over we're going to talk about data science challenges, Iguazio data science platform as a service over Kubernetes. Then Jacci is going to introduce NVIDIA solutions to accelerate data science with Kubernetes. And then we'll move on to a hands-on tutorials showing an end-to-end application, specifically real-time predictive infrastructure monitoring. And then, of course, time for Q&A. So feel free in the platform's chat and Q&A to just leave questions throughout the webinar, and we'll answer all of them at the end. I'm going to be here also. If you have any thoughts, concerns, anything, you can just contact me through the chat. That's it. Yaron, take it away.
Tamar, do you see my screen?
Yes, I do.
Good. So let's talk a few minutes about the challenges in machine learning and data science. So today, machine learning and data science is pretty siloed. You have essentially three domains of expertise. One is the data analytics or data engineering. This is where you prepare the data traditionally using data lakes, data warehouses, Hadoop, those kind of solutions. It's mainly around cleaning, preparing, and making the data ready for the data science part. Then there is the data science portion, which is usually using different set of tools, more oriented towards Python, R, TensorFlow, scikit-learn, etc., which are frameworks that are quite a bit different in philosophy and implementation than the ones in the data engineering side. And this is also where you would use GPUs because things like machine learning are very computation intensive, and this is where we'll see some of the advantages of GPUs. And data usually traveling not through like databases as you'll find in the data engineering. Usually people move around objects, CSV files, they do in-memory computation for many of those tasks. And eventually when the data scientist concludes his work, he generates a machine learning model. And that machine learning model is going towards deployment, usually in the form of a container that accepts all those different feature vectors and respond with some numeric results. Some of the challenges around that, when you're forming a machine learning model, it only accepts a vector of numeric floating point operators that tell the system how to run the algorithm. But when you're doing inferencing, you usually need real data, like a geolocation of a person, the customer balance or historical financial transaction of a user, weather information, or any other information, which is then transformed into that feature vector and acts against the model. So this is where we'll find interactive applications, usually web serving, HTTP-based applications, but they could listen on a stream, and they also need fresh data. This is also where we have some other challenges, like data that we've trained on in the model is usually not exactly the same data that we have access to in production. Maybe it's formatted differently. We're used to the notion of cleaning data when we're doing the research. How can we clean data when we're doing production? So there are many challenges that require some different approach to the data processing. And then obviously once we've used the model, we collect different types of telemetry, and we have to retune the model, whether the data changed or we've learned more information. It requires retuning. And the data scientists may need other types of data that he needs to sort of go back to the data engineers and ask for them. So this is a very siloed approach, which leads to very slow process and very slow time to production. Other key challenges that we see in that area is, first, people are sort of forced to recode. When you're moving to production, usually the data science code is not instrumented properly. For example, doesn't have security consideration, performance tuning, logging, exception handling, all the things that require more knowledge of programming, more skilled programming versus skill of data science. So what we see the need to try and automate the process of generating those models into production using various techniques. And we see that Python is sort of becoming a de facto standard for also running in production because you alleviate the overhead of recoding everything in a different language. There are solutions, the ones that we'll see, that allow you to accelerate and create more parallel Python code and allow you to essentially transfer the same code to production. Other aspects we discussed is, again, you're preparing a model that requires like 20 different features, and some of those features are not really available in production. So we need to find a way to fill those back. And we also need to make sure that when you gather information in production, you have decent latency. Because when you're doing learning, you can wait 15 minutes or a few days for someone to bring the data. If you need to respond to a customer request on the internet and provide recommendations, you cannot wait 15 minutes for a query to come back. And there are other challenges, we mentioned another one, which is the accuracy of the model versus the time it takes or the amount of CPU it takes to process an accurate model. Data security challenges, access to data both in production and during the data science phase. And all the tooling and infrastructure complexity where the data scientists need to now deal with all the aspects of wrangling data, getting access to data, installing all those different complex frameworks, drivers for GPUs, and scaling his computation. All those things are hindering his progress. So most of the data science will probably spend only 10, 20% of their time really doing data science. So with that, we've sort of taken a different approach, which is more continuous, sort of like continuous integration, continuous development in software. You can also do continuous development and integration in data science. So the first thing is to collect data. Instead of bringing data just when you request it, why not just like continuously bring the data, clean it up, and through different collectors, just fetch the data continuously from all the different sources. This is something that can easily be done using serverless functions, and we'll demonstrate that. The next layer in the solution is to develop. Most of the data scientists are using Jupyter notebooks, so think about having sort of a Jupyter notebook as a service, or also function as a service engines that allow you to write many different types of codes for ETL, for inferencing, for simulations, and other things that we'll see in a minute. And then once we've written some code, we need a cluster to train the model, to run continuous integration and development test, Jenkins. So we need a cluster. That means a lot of nodes orchestrated by some mechanism. In this example, we're talking about a lot about Kubernetes. And you also need all those different frameworks to be pre-installed, TensorFlow and PyTorch and Dask, and all those things needs to be accessible to those notebooks and functions that require them. And also, they all need some sort of a shared data plane because you cannot just tell a bunch of workers go process something without providing them the data for the processing. And eventually, once we've finished the training and build, we need to build some sort of an artifact that will run in production. This is this thing that accepts a web request or the streaming event, prepares the model, compares it against the model algorithm, prepares the data, generates the right feature vector, contrasts it with the model, and respond. So many companies that deal with the machine learning space, they essentially provide only the artifact that gets the feature vector and responds with some numeric values, and leave the problem of generating the feature vector for that model to someone else. And that leads to a lot of different challenges, like versioning issues. You've generated a new model that requires 2 new parameters. The code that feeds the model still is with the old version and doesn't provide those parameters. So you need a way to essentially package both those things, the code and the machine learning model, to something which is scaling, elastic, has its own telemetry, all that feeds into production. Talking about telemetry, it's very important to essentially feed all the telemetry from our machine learning artifacts, all the data that we've gathered from the requests of the users, all the information about how accurate our model was, all that can feed back into a database and from there to our data science workbench, and we could leverage that to relearn the model and refresh the model or fix things that we've stumbled into. So with that, essentially what we're providing is a fabric, which is slightly more modern than what you're used to in the Hadoop world. It's based on Kubernetes, and we'll explain in a minute what it is. And it's provided by Iguazio, our company, that provides this layer of sort of data science and analytics on top of Kubernetes, sort of a platform as a service offering. And NVIDIA, which provides GPUs that are very useful for cutting the cost, cutting the time you spend waiting for computation. And with that approach, you essentially gain three main benefits. One is develop and iterate faster. You can go and develop things in a matter of days or weeks instead of months and years. You can deliver much more accurate results in faster response time. And you can deploy it everywhere. You're not confined to a cloud provider solution that only resides in one place. You work on top of a standard approach, open source tools that can be deployed in any cloud, in the edge, or on-prem, even on a laptop. Okay, so before I conclude, so one of the components in the way our platform is designed is that you have, on one end, you could have different forms of external data. You may have your data in S3, in Hadoop, in other databases, Oracle. And then you have a Kubernetes cluster, which is standard. We can provide Kubernetes, but there's also a bunch of vendors providing their own Kubernetes. Or if you go to the cloud, there's Google Kubernetes and Azure Kubernetes and Amazon Kubernetes. On top of it, we provide a solution with three layers. The first layer is sort of a real-time data fabric or real-time database that's very unique because it's running on top of Flash, SSD, and provides the performance of an in-memory database and can impersonate as many different forms of database. The next layer above is all those different open source tools, as well as some third-party tools that can be integrated on top of that cluster. And those tools can essentially go and work on top of the shared data and cluster themselves, as well as provide collaboration. So one tool can write data, the other tool can read data, etc. And the upper layer is a full PaaS solution. So a user just authenticates itself, single sign-on, he has access to all those different managed frameworks underneath, and we'll show how it's working in a minute. One of the key aspects for data scientists is a notebook or the research environment. And one of the things packaged as part of the platform is sort of a managed Jupyter offering. It has four main attributes that we're going to demonstrate in a minute. The first, it's sort of serverless. That means that you just log in, you get your own private notebook, which is underneath the hood is sort of a container, a Docker container that is orchestrated with your persona and your data and your packages and everything that you required. If you're not going to touch it for a while, it's essentially decommissions itself and save all the resources and snapshots all your data and state. And the second major attribute is that from the notebook, you have access to many different forms of data and many different standard ways of accessing the data. So you can use Spark, you can use SQL, you can use time series data, you can shared file system, all those from a single notebook and in a very, very high performance. And another aspect is security. So everyone that logs into the system has credentials, and he can only see the portions of data that the administrator decided he can. So this allows teams to start collaborating. This allows data engineer to generate data and then share it with the data scientist. Data scientists can generate some results, and those could be monitors in like a dashboard. So this enables real collaboration without breaking security. The other aspect, as we mentioned, is the ability to go and access those scalable frameworks that reside on the same cluster. TensorFlow, Dask, a cluster of GPUs, PyTorch, Spark, Presto, all those different things are residing on the same cluster, and you're not confined to what the CPU of your own notebook. Many solutions out there, you get a nice beefy Jupyter notebook on a EC2 on a virtual machine, but then when you need to run a job, you don't really want a single VM. You want a cluster of 20 servers, potentially with GPUs that run the workload. So when it's all scalable and scale out, you can do that. And the last item, because the platform contains serverless functions and notebooks, you can essentially also toggle between the two. You can convert your notebooks into functions, and then just use the notebook as your IDE, as your development environment, and then submit things that not just listen on HTTP, they could be a cron job, they could listen on a stream of Kafka or Kinesis, all that from your notebook with a single command. So with that, the next thing that we discussed is the notebook, the serverless functions. Serverless function, if you haven't heard of solutions like Amazon Lambda or others, those automate your code. You essentially write some code, you write some definitions. For example, I need some memory, some access to CPU, I need some packages. All of that is being automatically orchestrated and launched on the cluster for you. The code is being compiled and generated. All the logging is instrumented, all the security is instrumented. If it fails, it's automatically recovering, it's self-healing. So that reduces a lot of the maintenance and DevOps overhead around software. What's unique about Nucleo versus other solutions like Amazon Lambda, first, it's open source. To just go and download it from GitHub, install it on anything from your laptop to a managed Kubernetes cluster. It supports extreme performance. You can do more than 300,000 events per second on a single process, and a lot less than a millisecond latency. Where other serverless solutions are usually in the hundreds of milliseconds and in the thousands of events per second. So about 100 times at least faster than the other solutions, and has a lot of integrations around data. It supports stream processing and checkpointing and other features that are very unique to data processing compared to the other Serve Lambda functions. And as we mentioned, it supports also one-click deployment from many different forms of code. You could just write the code internally. You can convert a container into a function, or a notebook into a function, or a Git repo can just go and build automatically and turn it into functions, or even cool template functions that allow you to automate the creation of functions. So with that, moving to Jacci to tell us a little bit about Kubernetes, and especially Kubernetes with GPUs.
So if you're new to Kubernetes, Kubernetes helps to simplify the use of clusters and GPUs. So Kubernetes is an open source orchestration system for Docker containers. It handles the scheduling onto the nodes in a compute cluster and actively manages workloads to ensure that their state matches what the user is intending to effectively declare as their intentions. Just like how the operating system abstracts away the various hardware resources, Kubernetes does the same with a cluster and abstracts away details about the actual infrastructure setup. The cluster's servers can be on-prem, in the cloud, or a mixed hybrid. Since the AI software relies on NVIDIA's GPUs to accelerate training and inference, it's really important. It's important that Kubernetes be GPU aware. So NVIDIA has worked closely with the Kubernetes community to integrate the NVIDIA device plugin, which exposes GPUs to Kubernetes and allows it to keep track of GPU health in the cluster. So some of the many benefits that Kubernetes provides for AI workloads is that it can simplify large-scale GPUs and accelerate AI training and inferencing. It allows the user to visualize and monitor GPU metrics and health in the cluster. And it also provides for automatic scaling to heterogeneous GPUs and multi-GPU nodes, and the ability to easily burst into the cloud with the same API across on-prem and every cloud provider. So Kubernetes really helps simplify the use of GPUs by offering users a consistent runtime and development environment for the GPU cluster. So as you can see, here's infrastructure and the code looking at, for example, a PyTorch training job. A key part of the data science is data exploration. To prepare a data set for training a machine learning algorithm, it really requires an understanding of the data set. You have to clean and manipulate the data types and formats, filling in the gaps in the data and engineering features for the learning algorithm. These tasks, they're often grouped together under the term extract, transform, and load. This ETL is often an iterative exploratory process. As the data sets grow, the interactivity of this process suffers when running on the GPUs. So to address the challenges of the modern data science pipeline, a suite of open source software libraries are built on CUDA. We call these cuDF for DataFrame, cuML for machine learning, and cuGraph, which we use for visualization. And these are designed to execute an end-to-end data science and analytic pipeline entirely on GPUs. The suite of libraries is called Rapids, and this aims to accelerate the entire data science pipeline, including the data loading, ETL, model training, and inference. This allows for a more productive, interactive, and exploratory workflow. And as you can see here, the Rapid software stack, it really helps to speed up by a factor of 50 times or more on a typical end-to-end data science workflow. Rapid uses the NVIDIA CUDA for high-performance GPU execution. What happens here is that it exposes the GPU parallelism and high memory bandwidth through a user-friendly Python interface. Rapids focuses on a common data preparation task for analytics and data science. This offers a very powerful and familiar data frame. And this API integrates with a variety of machine learning algorithms without costly serialization. Rapids also, it also includes support for multi-node, multi-GPU deployments, and enables scaling up and out on much larger data sizes. You can read-write Rapids data frames directly into Iguazio's database and file system. The cuDF is a GPU data frame library with a pandas-like API. So cuDF provides operations on the data columns, including the binary operations, filters, joins, and group bys. And it currently comprises the Python library, PyDGF, and the C++ CUDA GPU data frames implementation in live GDF. And these two libraries are being merged into cuDF. XGBoost is one of the most popular machine learning packages for training gradient boost decision trees, and native cuDF support allows you to pass data directly to XGBoost while remaining in GPU memory. And then finally with cuML, we have a GPU accelerated library of machine learning algorithms for singular value decomposition, principal component analysis, and density-based spatial clustering of applications. The cuGraph is a GPU accelerated library for visualization. And this particular slide is demonstrating benchmark results for cuIO and cuDF, and you can see that 50 times speed up when you look in terms of comparing the CPU nodes to the DGX2 here. Obviously, smaller is better. So we see time in seconds here. In the middle, you see the cuML for machine learning with XGBoost. And we have this showing at the bottom here what the CPU cluster configuration was. And then finally, the DGX cluster configuration, 5 DGX1s on an InfiniBand network. And then when we talk in terms of the TensorRT GPU inference server, we're looking here, you've built, you've trained, you've tweaked, and you've tuned your model. And you finally create a TensorRT TensorFlow model that meets your requirements. Now you need an inference solution, something that is deployable to a data center, to the cloud. So your solution should make optimal use of the available GPUs to get the maximum possible performance. The TensorRT Inference Server provides a cloud inferencing solution that's especially optimized for NVIDIA GPUs. This server provides an inference service via an HTTP endpoint, and this allows remote clients to request inferencing for any model that is being managed by the server. The TensorRT Inference Server is part of NVIDIA's TensorRT inferencing platform and provides a new software solution that expands on the utility of models and frameworks and improves the utilization of both GPUs and CPUs. It's based on NVIDIA Docker, and the container encapsulates everything you need to deploy a high-performance inference server in the cloud. These are the various models that are supported on the right-hand side, including multi-GPU support. And then I'll turn this back over here to our Iguazio team. What we're basically looking at is the flow here, and I'll turn it back to you to describe this slide.
So again, we mentioned that the machine learning model that is stored in that container essentially need to get data from somewhere. For example, it's a picture that needs to be extracted, potentially some time series data that needs to be collected and then fed into the model based on some windowing algorithm or something. And this is where a classic fit would be something like a serverless function. You get some events, some triggers, some HTTP request from a user. You manipulate it using a function in any language of your choice. It can be Node.js or Go or Python or Java, etc. And then you need to feed the request into the TensorRT through, it supports, as you've seen, a couple of protocols, HTTP and gRPC, which is slightly faster. The model itself can be stored in our shared persistent volume or shared database. So this is pretty integrated. And all the telemetry data that is collected from all the different containers and workloads within Kubernetes are also collected back to our time series database, which means that you can now actually use Jupyter to analyze information, just use traditional data science tools as well as dashboards like Grafana to analyze the results of the model and behavior of your infrastructure, which is also part of what Or will show us is infrastructure monitoring. Before I hand it to Or, let me just give you a short overview of the platform to get some orientation. Second. So within our platform, essentially you have all those different services. You have data management based on this real-time, extremely high performance database and file system. You have the built-in workbench based on Jupyter Lab that we'll see in a minute. You have serverless function, dashboards, and you can also load many different services. Like if you want to run Spark, you just choose from a menu Spark and you have Spark up and running. Then you click and it just works. You don't need to call your IT. You don't need any DevOps guys. It's really secure. It's working out of the box. And we support a bunch of different services that are pretty standard in the industry, including notebooks, etc. Now, when you need to build some functions, let's assume I want to run some artificial intelligence function. Take a simple example of natural language processing. Could go write a function. I already have one. I can also create a function from a template. I'll skip that just for the sake of time. If I go back to this natural language function, which was created from a template, again, I didn't need to change anything. I can go and edit the function to just click deploy. That automatically compiles the function, instrument the function, and deploy. You see, it's already 2 seconds. This function is already running on an HTTP endpoint, and I could do something here. Let's say I'll even have some typo, and you see it's translated to French. Another cool thing is that you have logging and instrumentation built in, so we can actually see through the logging what was corrected before the translation. We can see what's the sentiment of this sort of sentence, and we could do many other interesting things. We could go after more advanced functions like TensorFlow for inferencing, and this is a function that goes and runs the full image recognition algorithm within the function. It's not limited like Lambda, where you can only plug small models and it's pretty slow. In Nucleo, we could do many interesting things. And also in the configuration, I can essentially go and plug the machine learning model, the inception model, within the function. So then the model and the function, they can reside in the same container. That helps for performance as well as for versioning. I could mount file system and do that through mounting a file system into the function. And I have many other options here. And I could decide what triggers my function, whether it's just simple HTTP and then I just point what's the URL that I want to serve it from. If I like streaming, I could just point to a Kafka stream, and Nucleo would automatically do checkpointing, and all those aspects will be handled automatically. Okay, with that, moving to Jupyter, which is pre-integrated again in the platform, we'll move into a scenario that Or is going to present from A to Z. Maybe let's transfer to Or, and you start presenting the demo, and I'll explain it while you're starting. Okay, Or?
Yeah, Or.
Okay, let me get the screen.
So the demo that we're going to show until Or gets organized, I'll explain. Essentially, what we're showing is 4 phases of machine learning. The first thing is ingestion. We're not going to ingest real data. We're going to essentially use a generator that we've developed. It's also open source. It can generate all sorts of matrix and simulates the real data. It's actually generator can run from a notebook or from a function that just periodically goes and feeds data to really simulate a true situation. The next thing we'll do is exploration to show that we can essentially explore the data through various APIs and different tools. Then we'll run training in a parallel fashion using Dask, if you know what it is. And then we'll run inferencing, and we'll also show you how we run the inferencing in a serverless function. And there are other cool things that we can show you around how to generate Grafana dashboards and Nucleo functions automatically from within your data science environment. With that, I hand it over to Or. Yes.
As Yaron described it to you. So the general use case here is network operations. We are going to simulate a full deployment of multiple companies, where each company has multiple sites, multiple locations where they're deploying in, and multiple devices per location. Each device will show CPU metrics, latency, throughput, and packet loss. And through those metrics, we are going to show how we can quickly do a prediction, show whether there is an error going to occur, and of course, all the deployment cycle. So from the deployment point of view, we have the companies. So we'll have 2 companies. Each company goes with 2 data centers. And for each data center, we have 2 different devices. And as I said, we are creating the data here with CPU utilization, latency, packet loss, and throughput metrics. And of course, for the training later on, we're also labeling our data straight from the generator. Now, we're going to show two ways we can save the data that we generate. So we can both save it to CSV and save it on our file storage straight away. So the file itself will be available to everyone once it is saved, or through the next way, through our time series database. Now, what is good about the time series database is it's acting in real time, and it will allow us to share the results straight away. So whenever we save the data, it is already accessible to everyone else working with the database. So as you can see, very clean and easy, we are just creating our table, writing the data, and we can later on with one line, read the data from the TSDB, do some averaging, and show all the metrics straight away. Once we have the data, we generated a few samples, saved it into our database, we start to explore. So let's see how the metrics all look like. We load our data frame. We are working through Dask to enable us working on the cluster, parallelizing all the different work that we do, make it much faster to work with, and of course a few visualization libraries, so it will be nice to look at. And I'll show you the two ways we can load the data. So either we can load it, as shown before, through TSDB, select all the different metrics we want, and show it like this, or we can load the file. This is the raw file. So we'll have our timestamps, company, data center, device, and for each one, as we've seen before, utilization, latency, packet loss, and throughput.
Yeah, maybe to chime in for a minute, or I think to emphasize again why you would want to read from a database directly, you can see that Or did a very complex, go up a bit, Or did a pretty complex query with averaging. By the way, it also supports interpolations and other more complex query semantics for time series. And essentially it runs on a cluster in a very parallel way, based on low-level C code, and it's stored in Flash and all those nice things where this returns extremely fast just with the results. One of the challenges around pandas and pythons is the handling lots of memory. So if you're interested in just portions of the data, or someone else doing at least the cleaning or aggregation of your data, you just fetch a query to the database and you only deal with the result set, which is very powerful, and those queries run extremely fast.
It also allows you to work straight away on extremely fresh data. As you can see here, we're taking just for sample 60 days, but we can take the last 10 minutes, last 1 hour, and work on the freshest data that we have in our system. So this really helps when you want to explore the data as it's coming in. So let's continue. So it will be easier to look. I've taken a sample device here, just one device, so we'll be able to see the metrics in a good fashion. So we'll have a CPU utilization. As we can see, CPU goes normally around 70%. And we can see that we have some spikes here along the road. So let's try and just move in a bit to see how it looks like from a bit closer. Okay, so you can see we have a few spikes, and then we're getting into a real error part where we have about 100% of CPU utilization. So we can see that although most of the time we are around the normal ranges, there really are some spikes to the 100 where we suspect there is an error. We can see the description from the data frame. So we can see we're actually running around the mean of 76, and we can see the percentiles going in. So we can see that usually we really are around this mean, although we have a few maxes, which are those spikes that we saw before. We can look at the latency. the latency, which usually is around 0, as we can see here, also has some of the same spikes. Let's try and see, maybe they are on about the same ranges. You can see they're on about the same timestamps. But we can see again this same pattern of pre-error peaks, and then we go into the error situation, which really goes to the max of this metric. We have the packet loss, which looks about the same, behaves in about the same way. So we can think this really is some kind of an error, or maybe a cascading error going through our device. And to end, the throughput, which, as we can see, normally goes around 250 up to 300, and suddenly we have this drop to the 0 throughput, which can really show us that there is something going on. If we plot everything together, so we really can see a full device failure. Let's try and just zoom in a bit closer. So, as we can see, we have a few spikes in the packet loss, so we are losing packets. We see the throughput start to go down. In about the same time, latency goes up, and to finish it all, seeing that all the metrics go into a full error situation. Let's try and view some correlations around it, also to see if there is really something in the metrics and the errors. And as we can see, there really are correlations. Although we can see the throughput is in black, because, as we've seen before, it goes down whenever there really is an error, while the other ones goes up. So we can really see this negative correlation going on here. So after we explore the data a bit, we have it already on our time series database. Next step we want to do is to really train a model and see what we can get from it. So using Dask again, and Dask model selection with sklearn, let's try and do some model that will be able to predict those errors. So we'll start by loading the data again, as we did before. Okay. And after running the data, we want to start and do some feature. So here we do a very basic feature work. Let's just do some morning windows about the last hour, last few minutes. So we can see if the current sample that we have is above average. The algorithm will be able to learn how the averages go up and down, when there is an error and when there is no error. And through that, we think we'll be able to predict the error situation. So we've added everything to our data frame. And as you can see, we really start to see. The first ones are nonce, of course. The window function, they still don't have any window to fit. So we clean it up, as we said, because we don't want to confuse the algorithm with nonce. And we receive kind of the feature vector, the beginning of the feature vector, with the current sample CPU utilization and this 1 hour mean for it, to which we can work. Next up, after we've got a basic data structure, we really want to start the training process. So we get our feature vector, we get our labels, and then we do the train test split, which of course is also run through Dask, so everything runs on the cluster, which means that you can work with very large data set with a lot of partitions, and it will parallelize all the work for you. We'll save the data, so we'll have a reference back later on. And now, just to show a very simple classifier, we'll use a gradient boosting classifier. We'll add a bit of hyperparameters to test. We want to check the number of estimators, see if we can overfit or underfit, and generally how it behaves. And again, using Dask with DCV, we use their grid.cv. And what it does, given our cluster and threads, it will just put every different parameter configuration through our param grid, and we'll run it each one on a different node. So we'll be able to parallelize all our work and really save a lot of time on doing these computations. Without
And another point is, usually when we're talking about GPUs, it's hard to share a GPU. So one solution is essentially to create Dask, which is a cluster, sort of a clustered Panda version. And for every Dask worker, attach a GPU. So then when you submit a job, so you get, you pin those CPUs to a bunch of workers and everyone can share those GPUs. And like a scenario where you pin the GPU to a notebook and then only one guy can use this GPU at a time.
Exactly. So we've run the training process, and as we can see, we got a grid search CV. We can see that the best one that we got really was with around 5 trees. And let's continue. We want to see what the score that we have. We get 92% accuracy. And next on, we'll save the model. Once we finish the training, we got our best estimator. We really want to deploy this model into production and start predicting our anomalies, failures, and save some money. So what we do here, we save it into our file system, and we make it available through our Hadoop interface also. So it will be shared across everyone, and everyone can look and see this model. The next step, of course, is the inferencing. Once we got the training, we got our model, we want to start using it. So what we'll do, we'll load the model with this file name. We'll put it again in a parallel configuration. So it will be able to handle the most concurrent requests later on. For here, we load our sample data just to see it, and we'll run the actual prediction as a test. And you can see this sample is normal. As you can see, it really does match up to the metrics you've seen before, 74 CPU, 1 latency. We can really see this is a normal one. After finishing all this, what we want to show is how we can really deploy this on a serverless way, as we said, through Nucleo. So we have a Nucleo functions. Just a second, okay. Show it from here. So we have our Nucleo functions. In here, you can see our inference function. Our inference function is about the same as we can see in the Jupyter lab. But what the difference here is we do the following. Through Kubernetes, we can mount up our volume. And as we can see, I'm just sharing our basic data access point. And I'm letting it know where our model resides, so we can load it straight away. And when we go back into our code, okay, when we go into our code, we can load it straight away from there and run it. The next thing I want to show you is how we can deploy straight away to a visualization dashboard to Grafana. So we'll have here our Grafana demo. Basically what we've done, we've taken the table that we've saved before through our Grafana label, Grafana Maker packages on the system. We just put a new dashboard, telling it from which time, what data source. We show the table. We let it know what kind of graphs we want to know. So I'm creating here 3 rows. Each row will create a series taken from our Jupyter networks, metric Jupyter folder. And for each metric inside, as you can see, we will get 3 rows of 2 different metrics. And this is the results that we get. Building this
just to explain, instead of going manually and creating Grafana dashboards, you could take Jupyter with very few parameters and generate this beautiful dashboard through code.
Now, what is very nice that we can see, it also allows you to put some settings such as the shared sites. So once we really want to look at some point in time, it goes to all different points, so we can learn from it and explore it all at the same time in a synced view. Okay.
Yeah, so I will take the presenter.
Go ahead, Yaron.
Yes. Yeah, we wanted to show a few more things just before we open up to questions. I'll do it very rapidly because we don't have a lot of time. The first thing, we spoke a lot about rapids and QDF. We didn't really get to show it. One of the things that I'm doing here is on a Jupyter that is connected to also GPUs, is that using our APIs, this is essentially the V3IO frames client, is sort of the DataFrame provider for back or front end for our database. And then the only thing I need to change here, I need to tell it that the frame factory, the things that generates the data frames into the Python namespace is a QDF data frame. Then I could run a query on the same data that Or just built. So you can see it's sort of doing a select, and just I've taken only a few columns. And another pretty cool feature is that we can stream the data in, because we can sort of do computation and data fetching in parallel. Maybe we want to do some grouping or some processing as we're feeding the data. So what you can see is that I'm reading it as an iterator, so essentially streaming data from the database into the GPU. And then I'm also, just for sake of showing you it's really CUDA, you can see when I'm typing the type of printing the type of data frame, you actually see it's a QDF data frame and not a standard pandas data frame. Unfortunately, also QDF still doesn't have a nice print like pandas, but working on it. So still, QDF is very early, but it is pretty powerful and provides a lot of cool capabilities. Some other things that sort of we didn't get to show in Or's demo is that if you wanted to create this inferencing function with all its metadata, annotations, resource dependencies, you can also do that from within Jupyter. So I can create a function and just give it some environment variables, give it some configuration. Nucleo can also do cron jobs. So for example, let's assume I want to create a function that every 5 minutes generates something. So I just put some configuration. I can write a function, and then we have the Nucleo magic, where I just do deploy, and it will automatically generate the Nucleo serverless function for me, including all the package dependencies that I've defined, all the environmental variables I defined, all those sort of unique parameters that define the triggering and CPU required CPUs, GPUs, all that I can do directly from the notebook. Another interesting thing that Or discussed was Dask. So you can see that the Dask is actually a service on the same cluster. And it's interesting to look at the benefit of using parallel pandas versus standard panda. I've taken here some very simple example of just working on top of, just lots of trading information CSV stocks. And I want to, for example, just look at the close price versus open price, the gap across all of those. So I can calculate this on my own notebook, and then it takes me about 4.5 seconds. I could just go and do the same thing and submit it to the cluster, just doing a small, remember all those nodes in the cluster can share the same storage, the same database, same file system. So all the workers can work now in parallel on the same data, and then it only takes me 173 milliseconds. Now, if those workers also have a GPU, that number even goes down further. So all the guys that wait for the data science to complete and drink a lot of coffee, as a slogan from NVIDIA, you can take it down dramatically by creating more parallelism for the data, like in our case, as well as the computation, and use accelerators and shrink it considerably. Okay, so that's in general. Again, we can have on, and anyone that is interested in sort of a more detailed demo, we'd love to do that. We'll also try and share Or's work in GitHub, so we can, afterwards, I assume we'll shoot a mail and with more information on that. Okay, with that, opening to questions.
So yeah, we have a few questions. We don't have a lot of time, and whoever needs to go can go, and whoever has time to stay, then great, because we want to answer a few questions. So, Jacci, this one seems like it's for you. What makes this open source? Did you open source CUDA?
Yeah, so what really makes Rapids unique is executing the data science training pipeline completely on the GPU. So we've made, CUDA is not open sourced, but CUDA is the core of Rapids, and Rapids relies on NVIDIA CUDA primitives for our low-level compute optimization. But it exposes that GPU parallelism and high bandwidth memory speed through a user-friendly Python library. And these Python libraries are all open source. It's just that CUDA is not open source.
Thank you. Moving on to another question. Is there a way to run our code packages here? I think this is more for the Iguazio team.
Yeah, so one of the things that we can do on the Jupyter notebook is personalize the notebooks. That's something we've gotten a lot of requests, and you can do that. Essentially customize the container that the user gets, and we can put an R kernel built in. Now, not all the functionality that I've shown, like automating the generation of Nucleo or Grafana, is available from R, but a bunch of things are available.
Okay, next question. How does the inference function scale?
Great question. So, you know, in serverless functions, they're usually auto-scaling. So when you deploy a function, if you go to, for example, to Nucleo, let's take this natural language processing function. You can see when I'm going to the configuration, you can choose the number of replicas. The number of replicas is a range. It actually starts with 0. Starting with 0 means that when there's no load, the resource is going to be decommissioned, like Amazon Lambda. But you're not forced, like in Lambda, to have a slow start. You can start from a different number, and you can specify the maximum number. And based on load, the system will automatically scale up and out. In Nucleo, functions know how to scale up, meaning within the same process, introduce more threads, and scale out, which means it's allocating more processes for the job.
Okay, we're going to take one more question. What's the TSDB latency? And is there a difference when you call it with Nucleo?
So the latency measurement is usually, when you refer to latency, would be on the ingestion, because when you're querying, it really depends on what you're querying. Are you doing grouping? How many columns, etc. On the ingestion, what's nice about it is that essentially sort of zero latency, or measured in hundreds of microseconds to low milliseconds, because it's random ingestion. It's not like when you're building Parquet files, for example, which is a common way. You're essentially building the file, and then you're ingesting the entire file, and that could take a lot of time. And during that time, no one can see the results. Here, within hundreds of microseconds to milliseconds, the results are already available for anyone else to query the database. The query itself engine is much faster than going over files because of several reasons. One, the data is kept deduplicated in the time series database, so it's about 20 to 50 to 1 compression ratio. It's a huge compression ratio. Second, there is something called pre-aggregations. We don't store only the raw data, we also store aggregations on given intervals. So when the query is across a large window of time, we can go and use the pre-aggregations, and then the results are much faster. And another aspect is parallelism. The time series database works with a lot of parallelism across the entire stack.
Okay, so since we're running out of time, we won't take any more questions, but we promise to answer you all on email, and also feel free to contact us either through the email you got through the webinar or info@iguazio.com. We got a lot of questions about slides, so
maybe another, Tamar, just one last point. I see some of the questions. We have a cloud that anyone can do a trial on for free. So you can also request a trial in our website. And we are doing programs for universities, which include also sort of free software installed on your resources and things like that. So we would love to work with universities. We're already working with several.
Thanks for that. Definitely. And as I was saying before, we are going to share these slides on social media, on our website, so follow us. Thank you, Yaron, Jacci, and Or. Again, feel free to reach out to us for any questions, and we hope to see you next time. Thank you, everyone.
Thank you.
Thank you, everyone.